Morning, everybody. So I would be today talking about the multiphysics library that we have been developing uh, for biophysics processes in the terrestrial component. I'll show some initial development and applications. And before I proceed, I want to acknowledge my collaborator, Bill Riley, on this work. Um, So the terrestrial land surface models routinely do neglect some of critical multi-component multi-physics processes. And a few examples of these are uh, the the land models routinely ignore the transport of water through the entire plant soil continuum. That is, they only model vertical transport of water in the soil. But recent studies have shown that uh, hydraulic traits of root, stem, and leaves have a very significant impact on the response of trees to future drought. Another example of the process that is completely omitted is the lateral redistribution of near surface soil moisture as well as deeper groundwater table. We know that the topography will lead to hydraulic gradients. And there are some recent studies that are suggesting that this hydraulic gradient due to topography might mitigate how vegetation responds to drought stress. Um, Finally, the land model also does not account for the energy transported as water moves into the subsurface. Uh, this is critical, especially in the regions in or for permafrost fade, because what we see is as permafrost thaws and this the water starts to infiltrate, uh, uh, the heat associated with it uh, would accelerate the thaw of the permafrost. The E3SM project has acknowledged that these processes are critical, and we have worked on some of them in phase one, and we have plans of working on in phase two as well as in ongoing SIDAC projects. Um, then not only there are scientific need to have a library to solve these multiphysics problems, the current numerical algorithms in natively in ELM are inadequate to solve these tightly coupled multidimensional problems. Moreover, the current monolithic design of ELM does not allow even the existing physics to be coupled together easily. Lastly, the numerical implementation of processes in ELM is usually coded for a single spatial or single temporal discretization with a very fixed type of boundary and sourcing conditions. So it becomes very hard to compare the current implementation against various benchmark problems that are available in literature. Um, the challenges to solving these multidimensional multiphysics problems is not unique to the land surface community. Workshop on multiphysics problems for scientific disciplines across DOE was done in 2011, and various members of the E3SM community participated in this workshop. So this multiphysics problem library, which I'm calling MPP, it started with the notion that we are going to use a linear algebra solver coming from Oscar because we don't want to reinvent the wheel. And in this work, we are using PETC from Argonne National Lab to provide numerical solution of the discretized equation. Specifically, PETC's DM composite capability is very advantageous when you want to solve tightly coupled physics in an extensible fashion, and I will show example of this later in the slide. Finally, we are following an open source development, as well as the development is also open development. The code is open source and the development is also open. We are using freely available Travis CI for continuous integration on Linux and Mac OS X. And very recently, we have started to engage in solution verification via the method of manufactured solutions for the various physics. So for the remainder of this presentation, what I'm going to do is I'm going to break the presentation into 4 sections. 3 of them will provide applications, and last one is for verification. So the first application of this MPP library is to basically solve subsurface hydrologic processes. This is an example of single physics, that is conservation of water, and in single component, that is in just on the soil. And this is the variably saturated flow model that has been developed in phase 1, and the paper describing it is currently under review in GMD. The second application of MPP was to solve lateral redistribution of energy in the subsurface, and we applied this framework for the NG Arctic phase 1 study site. In this, again, it's a single physics, it's conservation of energy, but it is in multi-dimensional. Lastly, the third is actually an ongoing work in which we are using this same framework to now solve transport of water through the soil-plant continuum. So this is like the first application, but now it is in multi-component because we are solving conservation of water through various components of the soil-plant continuum. Finally, I'll give an example of the verification activities that we are now undertaking. So moving on to the first application, groundwater is approximately a 30% source of fresh water withdrawals for agriculture, domestic and industrial purposes. But the ELM version 1 of the model differentiated between the physics of near surface and deeper groundwater table. The figure on the bottom left is an estimate of water table depth globally. And as you can see, there is a lot of the region, a lot of parts of the world where water table is really very deep, deeper than 60 meters. And if we look at the graph on the right, this is showing a cumulative percentage of land grid cells with water table depth. We see that for the 13% of the grid cell, the water table is deeper than what the default depth of the soil column is in the land model. So we developed this variably saturated flow model, which has a unified physics treatment in the near surface and deeper groundwater table. We spatially and temporally discretize these equations, which leads to a set of nonlinear equations, which we solve using PETC. Finally, some sensitivity analysis of offline simulations showed that subsurface drainage flux has a very dominant control on the predicted water table depth. The parameterization for the drainage flux is shown here. It's an exponential function in which if the water table depth is shallower, the drainage flux is small. Oh, sorry, it's large. But as the water table goes much deeper, the drainage flux sort of shuts off. Uh, so we did the following simulation configuration. We discretized the column uh, to be deep up to a depth of 150 meters with 59 soil layers. Then we performed an ensemble simulations uh, uh, at 2-degree grid for 200 years for different values of F drain to estimate an optimal value of F drain for each grid cell. And finally, we performed an final offline simulation with the optimal value of F drain for 200 years. Um, in all of these simulations, we only looked at the last 20 years of these 200-year simulations. Now, an example of how the F drain parameter was estimated. This figure shows for one particular grid cell in the global simulation how water table depth was at the end of the 200-year simulation compared with F drain. So what we see is as the F drain value increases, the water table rises up into the soil column. The horizontal dashed line represents the water table depth that was uh, provided in the Fan et al. Dataset, and we linearly interpolated to get an estimate value of F drain. What we see in this curve is that this is a log-log curve, and the water table depth and F drain are linear until the most part, and then this linearity sort of breaks down. And we were interested in trying to understand why this happens. So you can look at a soil column and consider the inputs and outputs. The infiltration is the input, while the drainage and evapotranspirations are output. So what we see is the drainage flux becomes much smaller as the F drain increases. And at very high values of F drain, the water table depth becomes independent of the drainage flux. And the input, that is infiltration, and output ET sort of determine where this water table depth stabilizes. For another grid cell, where we were not able to match the water table depth as in the observation set of Fan et al. And again, the fluxes have a similar story. So when now we took the optimal F drain parameter and we ran the simulations, and here I'm showing the error in the simulated water table depth versus the Fan et al. Observation. The top panel is for F drain value, that is the default F drain value, which is spatially homogeneous, versus the bottom is our optimally derived F drain parameter. So first thing to note is that the optimal parameter simulation, all the cooler colors are gone, which means that we are able to match the deeper water table depth as in the observations very well. But we still have these hotter biases in which we are not able to accurately capture the shallower water table. The table below summarizes the statistics, and in all three metrics, the estimated F drain parameter significantly improves our prediction. But what this means is that since the simulation with optimal F drain parameter matches well the deeper water tables, Uh, those grid cells, for those grid cells, the surface fluxes are essentially not impacted uh, by this better prediction. Um, and as the water table depth is too deep and the surface is sort of cut off from the deeper groundwater table dynamics. So we really didn't see much difference in the surface fluxes with an optimal or a default F-drain parameter. Um, Now moving on to the second application of this library, we applied this in the NG Arctic Phase 1 study site, which is applied in a polygonal ecosystem, where the top figure on the right shows the microtopography for a horizontal extent of a 100-meter by 100-meter study site. What the image shows is a snapshot of snow cover over the microtopography, and you can see there are portions of the topography which are sort of jetting out, um, um, as they are not under snow. So what this leads to is that there is a heterogeneity of snow depth at the surface, which leads to a near surface heterogeneity in soil temperature, which propagates then down into the soil column. And we were interested to study how the inclusion of lateral redistribution of energy impacts this heterogeneity in soil temperature with depth. So we incorporated the lateral transport within the ELM model. The spatial and temporal discretizations leads to a set of linear equations in this case, and we solve with PETSI. Uh, the second figure here basically shows the sparsity pattern of the A matrix for the linear system for two columns which are disconnected versus the two columns which are connected. You see there are additional entries on the off-diagonal blocks indicating that these two columns are connected. We run 10-year-long simulations on a two-dimensional transect and included 1D versus 2D physics formulation. Next, I'm showing here are the results for comparison of simulated and observed temperature profiles for two regions in the 2D transect. One is the top panel is for the centers, polygonal centers, and the bottom panel is for the polygonal rims. So the centers have deeper snowpack during the winter, while the rims have shallower snowpack. So different colors are basically for different depths. The solid lines are for the observations, while the circles are for the models. As you can see from both panels, the model was able to accurately produce the soil temperature. Moreover, the model is able to actually pick the earlier freeze up for the rims as compared to the centers, and also was able to predict lower soil column temperatures in the rim than compared to the centers. And the differences between these two regions is just because of the thicker snowpack in the centers, which provide insulation. So then moving on to actually the difference between or the role of 1D versus 2D physics. This is a time series of spatial standard deviation of soil temperature with depth. So the top panel is for 1D physics, the bottom panel is for 2D physics. What you see if you focus on the first on the top panel is that there is spatial heterogeneity in soil temperature during winter, which sort of propagates down. And during the summer, as the snowpack recedes, this variability sort of disappears. But in the 2D model, what we see is that this heterogeneity in soil temperature gets dissipated much quicker than in 1D physics. We found that the inclusion of 2D physics did not impact the mean state, which is not shown here, but it definitely led to an overestimation of spatial variability. Now moving on to some of the newer ongoing work, and this is where the PETC's extensible DM composite framework is very useful to solve tightly coupled multiphysics problems. Here is an example of schematic example of how one might want to solve transport of water through various components, through the soil, the macropore, the root, the xylem, and the leaf. If one were interested, as we did in the first application, of only solving the vertical transport of water, we could write the system as one nonlinear system of equations where you provide the Jacobian and the residual and let PETC provide a solution. But we can, at the setup, tell PETC that there are actually two unknowns, and each of the unknown itself is a vector, one for the soils, one for the roots, and PETC has the capability to grow this matrix and provide you these off-diagonal and the diagonal matrices to fill up the entries. And similarly, you can think of extension to the xylem. So this framework provides us with an extensible framework to add these tightly physics components. So this is a ongoing work with Gil Bohr at Ohio State University and his postdoc Golnaz, which have developed a plant hydrodynamics model, Fetch2. We are starting to apply our model onto the study site at University of Michigan, where they have oaks and pines. The study period comprises of 3 years, from 2015 to 2017. As a pre-processing step, we generate vertical profiles of transpiration and then let model compute the actual transpiration based on the leaf water potential. The panels on the left are showing a leaf area density vertical profile of oak and plants, and then we have some time series of simulated transpiration. As you see in June and August, the cooler colors indicate that there is very low transpiration simulated by the models, and this is because the leaf pressures become really negative and the transpiration sort of shuts down. We did some comparison with the Fetch2 and our model simulations, and we have noticed that the VSFM is overestimating the transpiration. We have some ideas about why this is happening, and we are trying to look further into to sort out this discrepancy. Lastly, this is a very new addition that we are starting to do, which is a verification. I mean, we spend a lot of time doing validation by participating in a lot of MIPS, but we don't routinely do verification, which is, are we solving the equations correctly? And MMS is one approach to do model verification. The example here is you can pick a model. This is a steady state heat equation. You can come up with a solution or manufacture a solution for temperature and thermal conductivity as a sine or an exponential in space, and then you plug those expressions of T and lambda back into your equation, get a Q, use that Q to as a source and sink in your numerical model and solve for temperature. So what we did was, you can see that the temperature function in a cube looks like what it is shown on the left, and then we refined the spatial discretization of the model, and we wanted to see how the various errors, the L1, L2, L infinity, scale with spatial discretization. And we do get a slope which is corresponds to a second order accurate, and the model uses a second order accurate spatial discretization. So this is one approach of verifying the models. Presently, we have only done this for the thermal model, but we expect to do this for the hydrology model also. And that's my last slide. I'll take any questions.
No questions? Okay, then we'll thank both our speakers for taking the time to put together presentations. I know these video presentations are not quite the same as an in-person one where you can have more direct interaction with the audience, but we do think they're helpful for communicating both within the project and with the program manager. So Kai and Gautam, thank you again very much. And with that, we'll sign off. Thanks, everybody. Bye.
Thank you.
Thank you.